So now let's talk examples. So there is a download available for you, and it says this data set includes the highway and city gas mileage for a random sample of 8 cars. Assume gas mileage is normally distributed. It says that because we could see our sample is quite small, so we need to have a reason to assume that normal distribution of the SDOM. Construct and interpret a confidence interval. Also conduct an appropriate t-test to check your confidence interval interpretation. So here I have my example, and I'm going to example 1 tab right here. And here we have 8 models of cars, their highway miles per gallon, as well as their city miles per gallon. Here you have a lot of stop and go. Here it's like just zoom, zoom. And you could sort of see that there is a reason to consider these things as linked. They're linked because they come from the same model car, right? And so let's construct a confidence interval. And remember, in confidence interval, what we're going to do is use our sample in order to predict something about our population, right? So here, we will use our sample differences to say something about the real difference between these two populations. Here's the big step of difference when you work with paired samples. You have to first find the paired differences. So the D, the set of D. And that's going to be one of these. We'll take highway minus the city, right? So that's x1 minus y1, x2 minus y2, x sub 3 minus y sub 3, right? So here are all our differences. And we can now find the average differences. We can find the standard deviation of these differences and all of that good stuff. Okay, so let's find confidence interval. And this helps me to say, okay, what I need is my D bar plus or minus t times the standard error. And in order to find my t, I'm going to need, so I need my t, but in order to find that, I'm going to need degrees of freedom, right? And so my degrees of freedom, so here, it's just going to be the degrees of freedom of D, right? So how many differences I have minus 1. So that is count how many differences I have. I should have the same number of differences as cars, minus 1. So that's 7. Once I have that, I could find my T. Oh, I also need to find D bar somewhere along the line, and also SE. So let's find T. So T, I need to find T inverse. And I probably am going to assume I'm finding a 95% confidence interval. So my two-tailed probability is 0.05, and my degrees of freedom is right down here. And so that will be 2.36. So those are my sort of outer boundaries. And let's also find D bar, the average, right here. And I almost have everything that I need. I just need standard error. So standard error here is going to be S sub D divided by the square root of how many n's I have, how many differences I have. Right? So that's going to be the standard deviation of my differences divided by the square root of 8, because I have 8 differences. And that's 0.64. Once I have that, then I can find my confidence intervals. So the upper boundary, let's say, will be the D bar plus T times standard error. And the lower boundary is the same thing, except, shifted everything down. Minus T times standard error. And so my upper boundary is at 10.6. My lower boundary is at 7.6, right? And so to interpret my confidence interval, I would say the real difference between highway miles per gallon and city miles per gallon, I have 95% confidence that that real difference in the population is between 10.6 and 7.6. Now notice that 0 is not included in here in this confidence interval. It would be 0 if highway and city miles per gallon could be equal to each other by chance, right? There is less than 5% chance of them being similar to each other, to them being equal to each other. So because of that, I would guess that we would also reject the null because it doesn't include 0. But let's do hypothesis testing to see if we do really reject the null, right? Because since it doesn't include 0, I would predict that we would reject the null. So let's just go straight into hypothesis testing here. So first things first. So step 1, the null hypothesis. Null hypothesis. This should be that the mu of d bar. Actually, this might be easier if I just write this out. It's so weird when I type it. Okay. So here, let's do hypothesis testing. So first step is mu sub d. Oh, sorry. I need to say that this is my null hypothesis. Mu sub d bar is equal to 0. Highway and city gas mileage are the same. But the alternative is that one of them is different from the other, right? So they are different from each other in some way, and it's significant. They stand out. This difference stands out. So that would be that mu sub d bar does not equal 0. So step 2, my significance level, the amount of, so the false alarm rate that I'm cool with is very low, 0.05, two-tailed. Let's set our decision stage. Now I need to draw an SDOD bar. And here I put my mu as 0, right? Because the mu sub d bar will be 0. And let's also find the standard error here. So standard error here is going to be S sub d bar. And that's really the standard deviation of the d's versus, over the square root of n sub d, right? And that I could compute here. So actually, we've already computed it because we have the standard deviation of the d bars over the square root of how many d's I have. So that's 0.64. 0.64. What's my degrees of freedom? Well, that is 7, right? Because it's how many differences I have minus 1. And based on that, I could find my t, and I actually did already. My t is going to be plus or minus 2.36. Now let's deal with our sample. So when we talk about the sample t, what we really mean is what is the x bar of our sample, of our sample differences. So that would be d bar. I was going to put x bar sub d, but this is the simpler way of doing it. Minus the mu, which is 0, over the standard error, which is 0.64, right? And so I could just put this here. So I could skip directly to step 4, and I will compute my t. Sample t. And I should say this is my critical t, so I don't get confused. My sample t is going to be d bar minus mu over standard error. So that is d bar minus mu, which is 0, divided by standard error. And that's 14.3. Woo! Big T. 14.3. Right? And now I could also find the p-value. And I'm guessing, my p-value is probably going to be teensy tiny. Because if you're, out 14.3, I mean, that's really small. So my p-value is going to be t dist, because I want my probability. I put in my t, my degrees of freedom, which is 7, and I have a two-tailed hypothesis. And so that's going to be let's call it just 2 times 10 to the negative 6. So 2 times 10 to the negative 6. So imagine 0.00, so 5 zeros, and then a 2 at the end of that. All right. Given this teensy tiny p-value, much smaller than 0.05, we should say at step 5, reject the null. And we had predicted that we would reject the null because the CI, the confidence interval, didn't include 0, right? And so good job, confidence interval and hypothesis testing, working together. Okay, example 2. See the download again. This data set shows the average salary earned by first-year college graduates who graduated at the bottom or top 15% of their class for a random sample of 10 colleges ranked in the top 100 public colleges in the U.S. Is there a significant difference in earnings that is unlikely to have occurred by chance alone? Okay, so we want to know, is there a difference between these top 15% folks and the bottom 15% folks? And they're linked by having graduated from the same college. We wouldn't necessarily want to compare people from the top 15% of one college that might be really, really good to the bottom percentage of people from a college that might be not as great, right? So we would really want, from the same college, does it matter if you were in the top 15 or bottom 15%? So if you go to example 2, click on example 2, you'll see these randomly selected colleges and the earnings in dollars per year, salary per year, for the bottom 15% as well as the top 15%. Because it's a paired sample, what we want to do is start off with D, our set of D. So what is the difference between bottom and top? And we're going to get probably a whole bunch of negative numbers, assuming that top earners earn more than bottom. And indeed we do. We get a bunch of negative numbers. So if you wanted to turn these negatives into positives, you can. You just have to remember which one you decided as X and which one you decided to be Y, right? So I'll call this one X, and I'll call this one Y. X and Y just help me remember which one I subtracted from which. And I'm going to reverse all of these. And it's just going to give me the positive versions of this. Okay, so here's my D's. You don't have to do that, though. And let's go ahead and start with hypothesis testing. So step 1, this part I will do by hand. Okay, so step 1. So the null hypothesis says something like this, that the top 15% folks and the bottom 15% folks are the same. And so their difference is going to be 0. So the mu sub d bar should be 0. But the alternative is that they are different. And we are neutral as to how they are different. We don't know whether one earns more than whether top earners earn more than bottom or bottom earns more than top. We could use our common sense to predict that top ranking folks might earn more. But right now we're neutral. So step 2. Step 2 is our alpha level, 0.05 or significance level. And we'll say two-tailed because we're neutral. Step 3, drawing the S-dot. so the mean differences. And here we'll put a 0. And let's figure out the standard error. Sorry, just lost it for a second. Okay, so standard error here would be S sub d bar, and that would be the standard deviation of d over the square root of n sub d, right? We also want to figure out the degrees of freedom. So that's going to be n sub d minus 1. And we also want to find out the t. So those are all things we could do in our Excel. So step 3. So standard error is going to be S sub d bar. And that will be S sub d divided by the square root of n sub d. So that will be the standard deviation of our d's, of our sample of d's, divided by the square root of how many there are, and there's 10. Great. So here is our standard error. What is our degrees of freedom? Well, that's just going to be 10 minus 1, gives us 9. And what is our critical t? We know it's a critical t because we're still in step 3, the decision stage. We're just setting up our boundaries. So that's going to be t inverse because we already know the probability, 0.05 two-tailed, degrees of freedom being 9, and we get 2.26. So it's plus or minus 2.26. Those are our boundaries of t. Now, step 4, this will say, what's our sample t? And that's going to be our d bar minus mu over standard error. So I'll write step 4 here. And so I'll need to find t, which is d bar minus mu over standard error. So I need to find d bar for sure. And I already have standard error. So my d bar is the average of all my differences, right? And that's about $12,000, $13,000 a year. This is just right after college. Maybe some people are in grad school and stuff. All right, so I need to find the d bar minus 0 divided by the standard error to give me my sample t. And I'll write sample t so we don't get confused. So that's the difference between sample t and critical t. Our sample t is way, way far out. So 8.05, right? So this is actually, this is actually the average of the differences. So somebody is, well, we know who. The top 15% are on average earning $13,000 more than the bottom 15%. And the sample t gives us how far that difference is from 0, right, in terms of standard error. So and we know that that's way more extreme than 2.26. So now let's find the p-value. So we will put in t-dist because we want to know the probability. Put in our t, put in our degrees of freedom, and we have a two-tailed hypothesis. So that would be 2 times 10 to the negative 5. So our p-value equals 2 times 10 to the negative 5, which is a very, very, very tiny, tiny number, much smaller than this alpha. So we would reject the null hypotheses. And so is there a significant difference in earnings that is unlikely to have occurred by chance alone? Well, there's always going to be a difference in earnings between these two groups of people, the top 15 and the bottom 15%. Is this difference greater than would be expected by chance? Yes, it is, because we are rejecting the model that they're equal to each other. Example 3.